Okay, so another problem from practice problems 10. Let's look at the second one. This is kind of a real short one. We've got a ring with a space in it. So we've got a circular steel ring and is cast. It's made this way with this gap. If the casting is heated, the first thing they ask us is, does the width of the gap increase or decrease? And the second part of the question then says the gap is currently at 1.6 centimeters when the temperature is at 30 degrees Celsius. Determine the gap width when the temperature is at 190 degrees Celsius. So for the first one, does the width of the gap increase or decrease? Well, if you remember reading the section in your textbook that talks about what goes on in terms of size of openings and how the geometry and the form actually changes with heat, with this particular instance, the gap width is a linear dimension. So it increases in thermal enlargement as the temperature increases. So it increases and decreases the width. Okay, so it increases. So now let's look at what happens. Let's prove it mathematically. We're going to go from 30 degrees Celsius up to 190 degrees Celsius and look at how this in fact increases. So at 190 degrees, the length of the piece of steel that is missing or has been removed to create the gap is, and again, it's defined by that relationship for determining the length, the coefficient, and the change in temperature. So in this case, if we're looking at an initial length of 1.6 centimeters, and we then include all of our values here. We do have now here the coefficient alpha for steel. That value is 11 times 10 to the minus 6 per degree Celsius, and we're going to multiply that times the change in temperature. Okay, so there's not as many steps here as the previous problem, but you get the idea of what's going on. So that change is the temperature final minus the temperature initial, and when we multiply that times the coefficient and add it to 1 in the expression where we factored everything out, we end up with a value of 1.603 centimeters. So you can see it has changed with heat and has opened up the gap. Okay, so since this one was short, let's move to the second one, or the third one. Okay, in this one, a little chemistry. It says 1 mole of oxygen gas is at a pressure of 6 atmospheres and a temperature of 27 degrees centigrade. If the gas is heated at a constant volume until the pressure triples, what's the final temperature? Okay, so we go to our gas law, ideal gas law relationship. It says PV equals nRT, and we can then find, as we move our terms around, pressure over temperature is equal to the constant N times R divided by T. Okay, so if both N and V are constants, and that's what they told us in the problem, then as the gas is heated, the ratio of pressure to temperature then will give us this relationship. So pressure final divided by temperature final is equal to pressure initial over temperature initial. Okay, moving terms around so that we can solve for that final temperature. Initial times pressure final divided by pressure initial gives us a relationship now that we can put our values in. 300 Kelvin, 3 times the pressure initial is our final. They gave us that in the problem. Triple the pressure divided by the initial pressure. Of course, in this case, the pressure initials cancel out, and I'm left with 3 times 300 Kelvin and get a value of 900 or 627 degrees Celsius. The next part of the problem says if the gas is heated so that both the pressure and the volume are doubled, what is the final temperature? So we're going to heat the gas, pressure and volume double. What's the final temperature? We go back to our relationship that we used on the top. Temperature final then, just as we had it here, but now we've included the volume because the volume has doubled. So now when we start putting our values in, temperature final times twice the initial for the pressure, twice the initial for the volume, divided by P and V. Again, those terms cancel out, and I'm left with then a value of 2 times 2, or 4 times the temperature final. The temperature final we solved for up here is, actually we were given 300 K. Let's see, where is that? Okay, so we got 300 K up here, so 300 Kelvin times 4 gives us 1200 Kelvin, or 927 degrees Celsius.